Welcome to a new test and teardown video. This time it's a Polarad 11 gigahertz signal generator. Yeah, it covers from 7 to 11 and it's a model 1108. Maybe this M4 is important. I haven't yet figured this out. If I Google I only need this 1108. I think it is from about 1965. It is 20.2 kilos heavy. It's a 19-inch unit. And funny, you can flip the handles inside like that and make it a little tabletop unit instead. That is pretty cool. So the width is 43 centimeters, height is 13 centimeters, and it's 42 centimeters deep. But if you include the feet and the handles, it will be 48 centimeters deep. It's of course a tube-based resonator oscillator, and it's a mechanical tuning element in here. And I need to open and verify everything before I power this up. We got a little bit of modulation here. So there's only a square wave oscillator, an internal oscillator. And you can FM amplitude here. I don't think you can AM from here. It's internal FM. And you can square wave something here. But it doesn't say exactly what kind of square wave that is. This is a little bit weird. Okay, CV we know, and then you turn off the RF, AM, FM. That's probably those in external power. We got a little bit of power indicator here. So I think the idea is you adjust for calibration. So you adjust the power. Oh dear. There's also some mechanical here. Not only the calibration, that is weird. And then you have the attenuator. And I believe this is also a mechanical attenuator where the coupler moves in and out of the oscillator chamber. But all that we need to inspect. Foot storage. I don't understand exactly what that is all about. Here is the info sheet. And then it says here M4. And that is the model number. And it's of course from New York. And mains voltage is 230. So quite modern to see that. And there is a stabilizer input something here. I don't understand exactly what is going on. Ground. Yeah. Let's look inside this fantastic unit. I am a little bit surprised to see it is completely tube-based. Even power supply, oscillators, I mean everything is tube-based. I don't think we're going to find one single transistor in this unit. See all the voltage regulators and everything. There's a regulated high voltage and a regulated low voltage and voltage references and a little pentode to do the feedback and measurement and all that kind of stuff. And that is probably the oscillator for the modulation tubes. And the cable here goes into the resonator in one end right there, and the other cables goes all the way into the tube, and I bet there's a tiny little tube in here and a socket, DC filters and all that kind of stuff. All those capacitors, half of them they're probably in series because this tube runs on 1250 volts. And we've got two different voltages, a 300 and a 1250. And that will be here. And we got also a low voltage filament. And what else can I say? I am so impressed about the mechanics. You see those 3 glass fiber rods? That will be the push rods for the resonator that is inside here. And this whole sledge here moves up and down when you adjust the frequency. And then there is, of course, this readout that is connected to the dial and system and all that kind of stuff here. I think this is the shaft for the frequency. Let's try and move the frequency a little bit. See, that is the shaft, and this is the whole movement. And what I think here is the most impressive thing is this adjustment system here. There's a patent number on this, and the whole idea is, of course, at this point, so you turn this to the center frequency, and you can unscrew this one and rotate it, and then align everything so you got the exact correct frequency at this point, obviously, right? And then you move it to the minimum and the maximum frequencies, and there you have those 6 screws. And I bet they are oval or something like that, and then there's a thread, and the idea is you turn the screws, and then you bend or pull or push the aluminium. You can see there's a little piece of this is welded together. There's a little spot weld here, and then this point here, there's of course a little oval in the groove, and then you can fine tune in 6 points plus this one, of course, by rotating and all that. Amazing, genius way to solve it in mechanics. I totally love it. And then there is this shaft, of course, continues all the way down here to this little gearbox. And this gearbox, you can see a much finer gear down here. This one is connected to a potentiometer, a very, very big, high precision potentiometer. And that one is, of course, used for the feedback system and power leveling and everything. So that means we have a constant power no matter what frequency we are at. And all that is done, yeah, again, mechanically aligned. Then we have the output. So this is the output coupler. We got 2 different shafts. I will show what happens when I move the output power. See? This one moves the output power coupler in or out of the resonant chamber. But there's another one down there. And if I move the calibration at the front, this one here, then we move this other coupler. And that coupler here measures what is going on in the chamber. And that one is, of course, feedback to the voltage, power drive, and all that stuff for the tube. So it's actually very complicated, but it looks simple. And then we have all the alignments for, they say high and low and all those kind of things. And beam current, symmetry, meter calibration. Everything here is written, easy peasy access. Because I don't have, of course, any kind of written paper material. Yeah, it's full of capacitors and load resistors. Maybe we should try and open the... Yeah, we can also take away the bottom plate and then have a little look from the other side. Maybe we can see a few cool things. What is that? Got a really nice logo here on that tube. CEI. Nice EL34. Power pentode. This is also, I think this is the long high power one. You can also find them in a smaller version. And they are very useful for guitar amps. And the bottom also impresses. I mean, I am impressed. first let's look a little bit on all the electronics. So I think all those, they are located, I mean, you can see the black wire here that goes from one to the next to the next. That means, of course, they are in series to get the high voltage capabilities. So I think that will be all the wires from the main transformer. And look at the size. This is a whole handful. It's bigger than my hand. And then, okay, also these wires. And we got diodes, see? Because I didn't find any rectifier tubes. So we got diodes instead. And down here we got, let me see if I can get some little light here. This is probably the high voltage. This diode looks really weird. Maybe this is a little cooler, or maybe this is for isolation, whatever that is. It's just, what is that? This is another capacitor. And down here we got diodes. We got more diodes up here. And I mean, what is going on? There's not a lot of room here to do service. And there's a jack. What is the jack connector doing here? This is a normal 1/4 inch jack. Really? And oh yeah, over here in the mechanical department, it is easier to see this mechanical thing here. And the alignment resistors, or all the potentiometers for calibration, see, they want to put them closer than possible. So what they're doing is they're offsetting them to get more into the same room. Isn't that just cute? Oh yeah, and this is the frequency power compensation potentiometer here. Again with all the gearboxes and fancy things. Yeah, but I don't see any leaked components or anything that looks like it's blown up or whatever, so I feel we should power this up. Oh, this type of resistor here is famous for not working. I've seen them so many times and they always fail, so I will have a little extra look at that one. I forgot to say this little thing here. Sometimes I find these 4/15/68. So that will be a date. Look at that. Month, day, year. So I have now updated my little, I always make those little note sheets here for myself when I'm doing something. And in the beginning I wrote 1965, but now I corrected this for 68. So now I can update my info. And you can access everything much easier if you take away the side panels as well. See, this cable here is the output connected to the front panel N connector. It's still a little thin, flimsy cable, but of course it needs to be able to move a little bit here from the coupler. But there's another coupler down here, and that is the that somewhere at the end of this cable. I don't know if we can, yeah, here we go. So this is the reference coupler, and this one goes to this little unit right there. In here there is probably a little crystal rectifier, because they are wideband as crazy. I don't dare to open this one because it will destroy its calibrations and everything. Of course, if the unit blows up or if I'm not able to get any kind of outputs or anything like that, then I promise I will open and inspect this unit later. But right now it is just not in the cards to look at this. But there will be a little special crystal on a little ceramic disc, something like that, and a little capacitor to make it into a DC voltage, and then it goes via this BNC cable, or BNC connector here, and then this cable to the power reference calibration something right here. So I think I am ready now for the first power on test. What I want to see is, of course, that it lights up. We get light in all the tubes. We will get some power indication here. I'll put this in the middle. Let's just put it 7 gigahertz. And RF off first, right? Mains is applied, and then we flip it's using 100 watts. I expect when the tubes gets warm, we got nice light here. I got light and all fancy smancy things in all the tubes over here. All this looks really nice. I see some light in the voltage regulator, so I'm a little bit worried. I don't see light in that voltage regulator there, and not that one. And also not... This is probably not exactly what I expected. Let's try and flip the RF on here, and then it's probably gonna go crazy and something's gonna happen. Why don't I hear this relay? No way, man. There's a relay down here, and I was expecting this one to go clickety-clack. Yes, exactly. Here we go, 150 watts. Something definitely happens. But it didn't happen when I was flipping the switch. Now I switched the switch off, and it's still using 150 watts. So I think I want to power it off. Something is happening, and I want to go and get my thermal camera and monitor the temperatures of capacitors and stuff. Aha, that is not what I expected. Just wanted to show you this real quick. So with a thermal camera, you can much easier prove what is going on. We should see 4 tubes right here. See? Oh, and then suddenly it starts to use a lot of... Oh! Now I see the light. So we got a problem with something. It's repeating itself. It takes quite a long time. I am a little bit worried about that. But now I see the light in those, in that one, not... Oh, also in the back one here. So now it will probably pull this relay. So let's try and see. Maybe this is normal. Click. I don't see that one. Now it's probably heating up the filament. I don't see anything, and it's using 150 watts. But there is no indication here. This is not too good. I will keep monitoring. All this is good so far. I'll probably go and flip it and look at the other side and see if everything is good here, because I don't have any documentation, and I can see power consumption is slowly rising, and I get an alarm here. So I set it real low, so I should turn it off and monitor the other side. I got a little bit more news. I was able to find a little bit of manual, and I also found a lot of schematics. That is of course for a much older model, but the 150 watts is not wrong, and it is using 156 at the moment. And I'm trying to poke around with everything here. I don't get any kind of output, and I try the different settings for the power detector, and I don't get any kind of feedback to the detector and the regulator, and I don't get this relay going on and off. And I'm also measuring on the output. I adjusted this for 7 gigahertz. I just put my little baby here for 7 gigahertz in the center and 1 giga span. This one can do a lot of gigahertz, so we should be perfectly fine, right? And yeah, there's absolutely no output whatsoever. So back to the drawing board. I should definitely see the relay, but the power now the power consumption gets up. So now it's 162. That is good. This is what I want to see. Well, I'll be back. I don't know how good this is, because power consumption just keep going up slowly and slowly, but it is rising all the time. I mean, I get worried about this. In a minute we're gonna hear something say kaboom, and then it goes down like 10-12 watts. That could be the klystron powering up and down. But I'm a little bit worried about the power consumption just slowly going up. This tells me something is really, really bad. I was able to find schematics, well, not for this exact model I got, but for a similar model. And the power supply seems to be exactly the same way. So that's quite lucky. So if we look here at the schematic of mainly the power supply and also the klystron assembly, I kind of finally figured out what is going on in the power supply. First of all, this very, very long delay was puzzling me a little bit. And if we look up here in the upper right, we see 2 transistors, and we see a very high value resistor and a very large capacitor. So obviously you're having a very long charge time, and then those 2 transistors, they drive the relay. The relay then enables the series regulator, and this explains why only one of the neon-filled voltage regulators there is lit at power on. It is of course the upper left one that is lit at power on, and then nothing else happens, right? So until all the tubes, filaments, they are nice and warm and ready to go, then the relay pulls, and this enables, of course, V1, the series regulator there. And that is our minus 1250. And that shows, of course, also in real life. Then now we see light in that voltage reference tube. And this voltage, the minus 1250, is also used to enable the bottom highest voltage regulator. That one is making minus 1760 or something like that. And that one uses 2 other of those OA2 neon-filled regulators. And that is also what I see. They light up also. So I also took my high voltage probe and measured both of these voltages, and they are nice and fine and almost accurate. A little bit low, but just a few volts. So I really don't think it is a power supply issue. Then I went to the klystron connector. So there is a, if we start to look here at the klystron oscillator circuit, we can see a 5-pin connector, and they even named and numbered them really nice and fine, so we can figure out what is going on here. The fun thing is that if you look at the schematic here, it is the rotated, so this is this connector is probably seen from the back maybe, but I've easily figured this out. And then I measured all the voltages at the klystron, and all that is also perfectly fine. So there isn't any reason for this not to oscillate. So now I need to open the klystron and just see what is in there. Maybe there's nothing in there. So here is my little note about the klystron connector, and that'll be the 5 pins right there. It's easy to figure out what is what here, because there is one wire that is special, and this one goes to the top of the tube. The rest of the pins goes to the socket at the back, and that is easy to understand when you know a little bit about how these klystrons they work. And so that means this one is the reflector, cathode, filament, and then a steering grid. And there's only 10 volts on the steering grid in relation to the filaments and the cathodes. And then we should have 200 to 300 volts to the reflector. And if we look at my voltages here, I think it is very close to the optimal. Of course, I do not have super good resolution with my high voltage probe. It's plus minus a few volts, but I really think this is good enough to have this tube up and running. So there's probably something wrong in the tube. Maybe it's the connector, maybe it's not even there, because I think this looks not like the original. This cannot be the original, right? They would have used some sexy special bracket or something. So I better go and have a look there. This is the last thing that I can do for this unit, really. So that was almost too easy. And the fun thing is, I see this green. This is exactly the same kind of green color I see on these. So maybe this is the original. Really? And here it is. Our super nice klystron. I should be able to pull it real careful. Maybe I need two hands, because there will be a... No, it actually comes... It is a lot bigger than I thought. What is... Oh, so this falls apart. And there's supposed to be a... What the heck is that? So this is a rubber band that holds these in place. That is weird. But here it is. My beautiful, beautiful klystron. Of course, I verified the connections and the solderings and everything here. All that is fine. So, I mean, the only thing I can do is measure if there is a filament connection in this one. That's really all I can. There's no way on this planet I will be able to get another one of these. Oh, this is quite a high serial number on this one. It's also very, very heavy. But damn, it's beautiful. And it is correctly pin 2 and 4. That is the filament. And if I look at Radio Museum data sheet something, it says 650 milliamps, right? And it's 6.3 volt, and it's definitely working. So this is almost 4 watts. So I believe the filament is working, and that is all I can do for this tube. It's not even getting warm. I was able to find some more information in the manual about the klystron assembly. It's a fully exploded view, so I'll try and show it here so you can see how everything is built inside this klystron system. Other than that, I really can't show or tell any more about this unit. I think I've already said all there is to say about it. It is, of course, never ever going to work again, unless I magically find one of those klystrons again. One day, maybe, we'll see. So I will say thank you very much for watching. and hope to see you soon again. Bye bye.